Hello, this is the fourth video in a sequence of videos about C++ models. In this video, we're going to talk about the C++ object model. Of all the models, I think this is probably the most important. In order to, understand this model is important to use the C++ language effectively. So, in this, let's talk about the diagrams for a minute. In the top diagram, I've shown class relationships for a compound object D. So D inherits from a base class B, and B composes an instance of the class C. There is a friend object, a function or a class or whatever that has access to D's private member data. We tend, to try to avoid using friendship because it extends the region of encapsulation to cover the friend as well as the class. But occasionally we need to use it. So. D uses an instance of the U class, but D doesn't own it. Some other entity created it, perhaps the client created it. The client has created an instance of the D compound object, and it's doing that through aggregation. So let's talk about these relationships based on their strength. So this composition relationship indicated by the diamond with a solid color is a very strong relationship. It means that C is an indelible part of the B object, and we'll explore that a little bit in just a couple of minutes. Likewise, inheritance, indicated by this triangle, is a very strong ownership relationship. So this base is an indelible part of D. Aggregation is a weaker ownership relationship. D is not an indelible part of client. When client starts, there is no D object yet. The client may or may not decide to create an instance of D. And typically, it might do that by creating an instance of D on the heap and holding onto a pointer to D. But it might simply allocate an instance of D in one of its member functions as well. So that's also an instance of aggregation. And this using object has to get passed to D as an argument, a reference argument to one of these member functions, maybe a register function or something. And the client very typically will pass U to a member function of D so that D has access to it. Now let's see what those relationships mean. So I've drawn a diagram at the bottom of the bottom right-hand part of the page that shows the layout in memory of these instances. Now, I've shown it as a two-dimensional diagram, and of course, memory is a linear. Okay, all occurs in one dimension, but it's a little clearer. The things we want to talk about become a little clearer if we show them in two dimensions. So that's why I've done that. So first of all, we see here the B object wholly contains in its memory footprint an instance of the C class. These little bumps are the public member functions of C, and because they aren't at any of the boundaries, this says that only B has access to those member functions and can call functions on C. Likewise, B is resides within the footprint of the D class that inherits it. And its member functions are shown here at the boundary of both B and D to say that D inherits those member functions as well. This bump over here says that D is free to create additional member functions that aren't part of the B class if it chooses to. So, and the client, because it has an aggregation relationship to D, there's no overlapping of the memory footprints of the client, no overlapping of the memory footprints of the friend, no overlapping of the memory footprints of you. But this has very strong effects on the behavior of the classes, and we need to understand how this works. Because B is always a part of D, that means that B has to be constructed when D is constructed. It occupies part of the region that D occupies, and to have a valid D object, we must have a valid B object. And so D's constructor, whatever constructor of D we're calling, as its first act, calls the constructor, calls a constructor for B. And as the first act of B's constructor, it calls a constructor on C. Now, D can specify which of B's constructors it wants to call. B can specify which of C's constructors it wants to call. But the message here is that this always happens, that it's an indelible series of events. D constructor immediately calls B's constructor, immediately calls C's constructor, then the body of C's constructor executes, returns to B, the body of B's constructor executes, returns to D, the body of D's constructor executes. So it's a very, very strong relationship. And a lot of the way C++ behaves is determined by this inclusion model. You know, all of these relationships, the composition, so inheritance, composition, aggregation, using, and friendship, those 5 relationships are, you know, available for all classes. They apply to all classes, and they also apply to all structs. In C++, unlike many other languages, a struct is exactly the same thing as a class, except that a class by default has private access, and a struct by default has public access. So the mental model is typically a struct is an implementation detail and maybe mostly carrying data. Its function is to mostly aggregate together, you know, coalesce a set of values, but in truth, they both behave the same way. A struct can have a constructor, just like classes can have constructors, and so on. So that memory footprint is a very, very important part of the C++ object model, the dominant part of the C++ object model. So, you know, this just reiterates what we've said. When B is constructed, C is constructed, and you know, C resides right in that memory footprint, and the same thing for D. These are required events. They have to happen. There's nothing we can do to avoid that sequence of events happening. The language guarantees it's going to happen. And that means, because of this inclusion model, that this entire region is properly constructed. We often use initialization sequences to determine. So B can use an initialization sequence to decide to specify which of the C constructors it wants to call, and D can use an initialization sequence to specify which of B's constructors it wants to call. And initialization sequence looks something like this. So for the point class we looked at back when we were looking at classes, the point constructor uses initialization sequence for its data member name, and it just specifies it, passes in the name, and then uses this initialization sequence here. And very often constructors may be nothing more than a set of initialization sequences with an empty body. For the point class, we needed to do one thing that we couldn't do conveniently in an initialization sequence. We needed to reserve space for the n coordinates. So, you know, if that You know, if you've forgotten, that doesn't make sense to you, go back and look at the video 3. We talk about the point class in some detail. Okay, the last thing that we want to emphasize here is value types. C++ is unique in the way it treats value types. So the value types have instances that can be copied and assigned. And the thing that makes this unique for C++ is that they can also be polymorphic types. They can have virtual functions. They can have constructors and destructors. In many languages, a value type can't have constructors and destructors or virtual types. In C# and Java, for example, it's that way. The D language has value types that can be implemented with user classes, but they can't can't be polymorphic. They can't have virtual functions. So C++ is unique in that form. The new, relatively new language, Rust, does some really interesting things. You can create value types with Rust. Rust doesn't support inheritance in exactly the same way that C++ does. Instead, it uses something called a trait. And, you know, eventually I'll get around to doing a few videos that deal with Rust when we have the time. But anyway, for now, this kind of value type is unique to C++ and a very, very important part. So C++ was designed from the beginning to support the creation of user-defined value types. For a class like point, whose data members are a string and a vector, these both have correct copy and assignment semantics. They were designed to be that way. All of the containers in the standard template library, like vector, have copy and assignment, correct copy and assignment semantics, and string is the same thing. It has correct copy and assignment semantics. And what that means is that we don't have to supply in this point class a copy constructor and assignment operator, because the compiler, if we do a copy operation on a point class, the compiler, because we haven't implemented a copy constructor or an assignment operator, the compiler just goes and does member-wise copying of name and coordinates, or member-wise assignment of name and coordinates. And we talk about those as compiler-generated operations. If the class had a data member that didn't have correct copy and assignment semantics, for example, a pointer to something on the heap, if we were holding a pointer to some collection of data on the heap, then we would need to create a copy constructor, an assignment operator, and a destructor for the class to properly manage that pointer. So basically the rule of thumb is, if your class contains just primitive data, ints, doubles, and things like that, strings, and STL containers, then you don't need to define a copy constructor, assignment operator, or destructor. The compiler-generated operations work just fine. If you have something like a pointer to the managed heap, or you may have some type that isn't copyable, then you need to supply those operations as member functions of your class, or you can mark them as those. You can declare those operations and mark them as delete to indicate that this class doesn't support copying or assignment. But the way this point class is created, it does support assignment and copying, and we didn't need to write those operations because these guys have the correct semantics. So C++ was designed from the ground up to support value operations, copying and assignment, because if you didn't provide copy and assignment operations, the compiler will supply them for you simply by doing member-wise copying or assignment. And it does the same thing with bases. If point was derived from a base class, then the compiler would copy the members in the base as well as copying the members in the in this derived class. So C++ was designed to support value types by providing compiler-generated copies and assignments, and also allowing you to overload the copy constructor and the assignment operator to provide your own semantics if the class data members need that. Very, very, very useful, important part of the C++ programming language. Okay, we're going to stop here. The next video, video 5, will deal with polymorphism, consequence of inheritance, and a very useful part of the language. So with that, thank you for listening to the video, giving us your attention, and I hope to see you in the video 5 that deals with C++ polymorphism. With that, sayonara.